Welcome to Fort Collins Comic-Con. I'm Nick Armstrong, the lead organizer. Behind the scenes, you won't hear him or see him, but it's Jeff handling our live stream. So thank you, Jeff.
Welcome to Fort Collins Comic-Con. I'm Nick Armstrong,
That's where
the lead organizer.
Hearing us back. That's okay. That's my fault, I think. There we go. Live streaming. Welcome to 2020. So what I will say is we have an amazing array of scientists here today. It's the Ask Me Anything webinar, and you can jump on live, any of our streaming platforms, ask us questions live, and our scientists will answer them for you, or they'll make stuff up. It's one or the other. We're not sure. CC Petersen, who is our amazing science coordinator, not just for us, but also for Starfest in Denver. If you've been there, all of the amazing science panels come from her as well. So CC, why don't you kick us off with some introductions? Why don't you start, and then we'll just go down the line.
Okay, well, so this year I gathered together three people that two of you have actually been at Denver Starfest before. And in fact, I ran across Erin MacDonald at Starfest when Kathy Walker came up to me and said, "Don't you know Erin MacDonald? She also talks about science." And I had never been to one of your talks because I'd always been either coordinating something else or running around. So then I gathered her into the crowd, and she's been part of our Starfest and Fort Collins Comic-Con crowd for quite a while. You want me to talk about my and then I'll talk about everybody else. So Ken Carpenter is a scientist at NASA Goddard Space Flight Center. He works on Hubble Space Telescope and also on the Nancy Grace Roman Telescope, which will be launching. Well, he'll tell us that when that is sometime. Probably after James Webb.
That covers it pretty well. But proceed.
Well, we said that about James. Well, James Webb stands for Just Wait Space Telescope. Anyway, and then Dr. Claire Raftery. Dr. Claire here is part of the National Solar Observatory, and she is. She just gave a great talk about the sun, and I think I met you at an REU experience at CU because. Every once in a while, one of my old lab partners from the Laboratory for Atmospheric and Space Physics calls me and says, "You want to come and talk to our REU students about careers in science?" So we kind of got together and did that. And then Dr. Erin, I have to tell a story about Dr. Erin. This is really great. We were doing a presentation of one of these panels just like this at Starfest. And somebody asked a question. She's an expert on gravitational waves and all kinds of things like that. And you can tell us about why you left gravitational waves. But somebody asked a question about dark matter or dark energy or something. And as one, every other panelist turned and looked at Erin. And she's going, "What?" And I was sitting there dying laughing. You know, we're supposed to hold it together in front of everybody, but it was great. So Dr. Erin did work on gravitational waves. She went to school in Glasgow, Scotland, and is now currently working on, geez, how many, like 10 to the 6th Star Trek shows now? Something like that.
Feels like that. It's only 6, but yeah, it's a lot.
Yeah. Yeah. So, and she'll be able to talk about that a little bit without giving away any spoilers, because we all know season 3 of Discovery is coming up. So anyway, I got started in science, well, really as a kid. My dad took me out to look at the stars, and I just kind of went from there. And when I went to graduate school, I thought I was going to study Mars. And when I got somebody to actually take me over as a graduate student, is a fellow named Dr. John C. Brandt, Jack Brandt to all of us, who he put me immediately to work studying comets. And the outcome of 4 years of my life was this book, which it's really hard for you to see. Oh, yeah, I can't make you see it. It's called the Internet. It weighs about 10 pounds. The International Halley Watch Atlas of Large-Scale Phenomena. And for that work, I did astrometry, which is basically measuring scales and orientations of about 2,500 different pictures of Comet Halley that were taken from 1985 through 1986. And then we used that to study changes in the plasma tail, which is why I was interested in the solar work you guys are doing, Claire. And then at the same time, I was also studying science journalism. So when I got out, I ended up working at Sky and Telescope for a number of years. And all through all of this, I've spent a lot of time writing science content for planetariums and science centers, and recently I've started working on museum exhibitions. The last one that I worked on was in Shanghai, China, and it was for a place that's, I think, going to open up in January, the Science and Technology Museum in Shanghai. And they have 2 planetariums and a giant screen theater and 55,000 square feet of exhibits. And so that was a huge project to work on. So from all of that, basically you can get that I write about science. I like to write about science. I like to talk about it. And I like to bring it to places like Fort Collins Comic-Con and Starfest. Ken.
Hi, as Carolyn said, I work at NASA Goddard Space Flight Center. My day jobs are working on Hubble Space Telescope and on the newly renamed W1st, which is now the Nancy Grace Roman Space Telescope. I'm a project scientist, one of many on both projects. And basic role of my job is to represent the science community to the project management and make sure they worry about the science that's being produced by the telescopes, in addition to cost and schedule, which of course they also have to track and control pretty carefully. So that's been fun. I started working on one of the original Hubble science instruments way back in the mid 80s, which is where I first met Carolyn, the Goddard High Resolution Spectrograph. And then after a couple of years moved up into the project and have originally agreed to work for that for about 3 years. It's like, I don't want to get, typecast into a certain role. And, here I am 30 years later, still working on the telescope because it's been such a blast and such a run. And in part, they give me time to go off and do other things. So in addition to—
Yeah, you want to tell them like what?
Yeah, well, and in addition to working on science research, which is always great, I've been able to go off and study future mission concepts. At one point, I was studying an experiment to go on International Space Station to see if we could robotically assemble a telescope from pieces in orbit, and look at that as a future way for doing that. And that went gangbusters for a while until we fell into the place that you never want to be, which is between disciplines at NASA. When you're trying to get human spaceflight and astrophysics and heliophysics to all work together and to fund you jointly, you always get not unless you do it first. So we got through the initial design phases and we got to the, oh, I'm not paying for you unless they do. And we didn't go anywhere with that, but it was fun to work on that.
I thought you guys at NASA all got along. Wow.
Yeah, we do, but cross-theme stuff, danger, Will Robinson, danger. But something else that I did work on in terms of future mission concepts was a idea for a space interferometer where we would fly 30 1-meter diameter mirrors together like the Blue Angels in formation, have them co-point at a target and direct their beams to a combination spacecraft, so a 31st spacecraft. And this is very large scale. We're talking about a 500-meter virtual array that these individual mirrors move around in, and then the collector spacecraft might be 5 kilometers distant. But the idea is to get an aperture that's big enough to resolve features on solar stars out at maybe 4 parsecs or beyond, which is why I knew the answer to the questions that someone asked right in the previous talk. Just happened to be right up my alley. So we did, that was in part of what was called vision mission studies in the early 2000s, where the then NASA administrator was really excited about really stretching, finding stretch goals and really dreaming big. And then the web problems started, technical problems started happening, and they sort of pulled back. So let's not dream too big until we get web into space and working. So that's sort of quieted down in recent years, but we still hope to fly it after some of the other future missions. There was an interesting experience recently. There was an opportunity came out from what's called the NASA Innovative Advanced Concepts opportunity. And they said, we want you guys to think about or send in proposals for what you might study to do, given that there might be a human infrastructure on the surface of the moon. If there's already a base there with people around, what might you do scientifically? So I put in a white paper to look at building this interferometer on the surface of the moon instead of in deep space. And this is a multi-step process, and who knows if you're going to make it all the way through. But I just got a letter the other day telling us that we were approved in step A, which doesn't give you any money or anything, but it gives you the privilege of putting in a real proposal for step B. So that's we'll be doing that over the next month, proposing to do a study, not to actually build the interferometer quite yet, but we want to do a study over the next year to see how we might design it and whether it's feasible to do it given existing lunar infrastructure or not. So it's kind of That's exciting, fun, scary. Now that, wait a minute, I put in a proposal and they accepted it. That means I got to do it. So yeah, be careful what you ask for, kind of thing. Anyways, I could talk for forever here, but we should let somebody else say what they're doing.
Dr. Claire, you're next.
All right. Well, thank you. Thanks for having me today. As Cece mentioned, I gave a talk earlier on today about some of the details of what I've been up to lately, but my career started, I'm from Ireland originally, from Dublin, and I did my undergrad and PhD work at Trinity College out there, where I discovered solar physics. I wasn't really too aware of it before I started my graduate work, and I was very lucky at that time to spend most of my summers working where Ken is based at Goddard Space Flight Center, which for an Irish kid was a really big deal to be allowed to go to NASA to work for during my graduate years. So that was really awesome. After my graduate school work, where I was focusing on trying to find the connections between solar flares and coronal mass ejections, I moved to the Space Sciences Lab at UC Berkeley in California, where I was a postdoctoral researcher for a while. I worked on the RESI high energy satellite mission, and I was a member of their science team there. And while I was there, I started to get itchy feet, and I started to realize that doing straightforward research wasn't really what I had expected it to be. When I was younger, I had wanted to be a hairdresser, a teacher, or an airline pilot, and somehow I ended up as an astrophysicist. And so I set about trying to figure out how to realign my goals, my work with how I wanted to spend my time. And lucky for me, I worked in a place that had a thriving outreach department, which before then I was completely unaware of. And so I was at a conference, and a friend of mine from an entirely different institute in an entirely different state, I was telling her that it wasn't so much I wanted to do science, I wanted to figure out how to help people be excited about science. And she's like, there's a whole team dedicated to this down the corridor from you. So that was a great moment. And I proceeded to work with the multiverse education group at the Space Sciences Lab. And over time, gradually shifted my career from research into full-time education and outreach. And then a job opportunity came up at the National Solar Observatory, which is a federally funded research and development lab dedicated to running and maintaining solar physics telescopes all over the country and the world, really, on behalf of the National Science Foundation. And they were looking for somebody who, I'm pretty sure they had gotten my resume and had just written the job description to my resume, because it was almost a perfect fit for me. So thankfully they saw that too, and I got the job in 2016. So since then I've been running the outreach and education department of the National Solar Observatory. And so I'm based in Boulder, Colorado, and we have a telescope that we're almost finished building in Maui, Hawaii, and we also have a worldwide series of telescopes in 6 different locations around the world. So this is right now I'm working on the National Science Foundation side of things, but when I was in Berkeley, I was heavily involved in a number of different NASA missions. So I was as part of the science team for the RESI satellite mission. Then I was a project manager for the education programs of the MAVEN mission, which is a project out of the Laboratory for Atmospheric and Space Physics in Colorado. So strangely, when I left, when I left my old job, I no longer worked with the people who are now based upstairs from me. And I also ran the education program for the ICON mission, which is a mission dedicated to studying the ultraviolet emission over the equator. So unlike the aurora, which happens at the poles, this mission happens over the equator, and not much is known about it. So they've just launched a satellite to study that. So I've had a pretty varied set of opportunities, and every one of them is more exciting than the next, or than the last, I should say. So yeah, I've been really lucky to get to where I am today, and I get to split my time between Boulder, Colorado, and Maui, Hawaii. It's a hard life. So thank you. Thanks for having me today.
Thanks, Dr. Claire. And Dr. Erin, you're next.
Hi, happy to be here. So yeah, it's kind of mentioned up at the top, Fort Collins is my hometown. I was born and bred in Fort Collins. So I'm really happy to be a part of Fort Collins Comic-Con again, and to be on a panel with all of these amazing people. I met Cece and Ken
both, as mentioned, from the convention scene, but Claire and I actually met in graduate school over on the other side of the pond.
Other side of the pond.
It's great to come back together and those random-ish encounters.
It's a small world, right?
Yes, exactly. So it's fabulous. We've come a long way. It's so nice. And but yeah, so my background is in gravitational astrophysics. I did my undergrad in Boulder at the University of Colorado in physics and mathematics, and I was studying radio astronomy, searching for cold hydrogen clouds in the local universe, and then moved into gravitational waves for graduate school. Joined the LIGO collaboration through the University of Glasgow, did my research mostly on searching for continuous gravitational waves that were coming from neutron stars. And then my postdoctoral work at Cardiff University, still with the LIGO gravitational wave collaboration, was more focused on gamma ray bursts. So neutron stars colliding and cool stuff. But I need to caveat that I left LIGO a year before their Nobel Prize winning detection. So when I was doing it, it was all theoretical. We had no detections at that time. But my official story is I helped loosen the jar lid. So that's what I like to say for that one. And yeah, since then, I left academia, moved back to Colorado, started working a little bit in outreach and education. So I worked at the Denver Museum for Nature and Science. I worked at the Colorado Community College system as an adjunct professor, teaching intro to astronomy and intro to physics. Then I started working as an aerospace engineer, doing systems engineering as a technical advisor for the federal government, which was a interesting, fascinating job. Weirdly, not my research so much, but the skills that I had learned over the years applied a lot more than I was expecting. And that was a pleasant surprise, but also the ability to communicate science to people at different backgrounds and at different levels. And that really came into play a lot in my job in that environment as well. While I was working as an aerospace engineer, I was giving a lot of outreach talks because I missed teaching a lot at Comic-Cons, such as Fort Collins Comic-Con and Starfest Denver, as well as Awesome Con, Dragon Con, Rose City Comic-Con, all those other fun conventions. They're all great. A lot of us are hurting this year, not being able to go geek out in person. So I'm glad that we were able to do this at least. And, but through that's where I started teaching more about the science, but using science fiction to teach science. So I started putting my stuff on YouTube. Dr. Erin Explains the Universe. I started having my Twitch channel as well. And through that's how I started to meet other creatives, writers, actors, producers, showrunners, and then moved out to Los Angeles for both personal and professional reasons, but continued working as an aerospace engineer, but then had the opportunity to start working more with Star Trek. So I started going as a speaker to the official Star Trek events, such as Star Trek Las Vegas and the Star Trek Cruise. And then last year, they brought me on to be the science consultant for the Star Trek universe. So all of the current shows in development, which right now are 6. And no, I'm not giving any secrets away. That is, a lot of people are doing that because they're not all airing right now. But we have Lower Decks, and then as CC mentioned, Star Trek Discovery. There's also the announced Section 31 show. There's also the recently announced Pike show, Strange New Worlds. Then there is the Nickelodeon show, Prodigy, and then I know that there's another, Picard. Picard. Picard's
Can't forget Picard.
I know. So none of the stuff I've worked on has aired yet. So I unfortunately won't be able to share any trade secrets with that yet. And then, yeah, as mentioned, Discovery Season 3 starts in October after Lower Decks finishes, and that will be the first stuff that I've worked on. So I'm very excited to see that. And currently I'm not working as an aerospace engineer anymore. Transitioning my job into the entertainment industry through some great mentorship from the creative people that I've been able to work with, moving more into a story editor position and a writing position. And I'm excited to see what comes of that. So this little astrophysicist took a hard left turn. But anyway, thank you, Nick.
Yeah.
A lot of us do that.
So along with that, what is your favorite sci-fi series right now, if any? It's a question for the whole panel.
Okay, I'll answer first because I'm repping it right now, but I love Lower Decks. I love it. It speaks to every part of my soul in many, many ways. But I am biased. I mean, things the Firefly, Battlestar Galactica, all of those are I can quote those pretty well. So
I adore
oh,
so
go ahead.
many of the different ones, including, as you mentioned, Firefly specifically, but Battlestar Galactica, Babylon 5, all those are great. But my favorite has actually got to be Discovery. And I love your shirt, by the way, there, Nick. I just love what they've done. I know some people had trouble with the darkness in the first season, but if you work your way through that, boy, the payoff is just stupendous. And season 2 was some of the best Trek that I've seen in any series. And I don't know if I'll get hit by lightning from fans out there, but I just think Discovery is firing on all cylinders. I can't wait to see the next season of it.
Yeah, you know, Jim Bridenstine is watching this. He's going to have a chat with you. Yeah, actually, boy, you know, on television, it's hard because Picard was a little hard to get into in the beginning, but it pays off in the second season, and Discovery was the same way. It's kind of like between the two of them. I also read a lot of science fiction, and I'm still very particular to Lois McMaster's Vorkosiverse, basically her Vorkosigan books. I did read that they might try to make a movie out of one of them, and I'm scared to death they'll mess it up. But they're really good, so that's kind of where I'm at.
I grew up watching some of the Star Trek early shows with my dad. Next Generation is a special place in my heart as a result of that, but I think it's got to be Battlestar Galactica for me as well. I can pretty much quote that one as well. That was a turning point for me for sure.
You know, Erin, you were telling us one time about Scully and how she inspired you, but also, and I realized I was just reading in Gina Davis's foundation that she had people come and talk about the Scully effect, but you also had kind of a turn on with the captain in Voyager.
yeah,
and
Janeway.
I always thought she was really fantastic.
Yeah, it's so important when we talk about, as scientists all here, talking about our favorite sci-fi, but a lot of that is inspiration. A lot of it, we became scientists because of science fiction. And yeah, for me, it was the X-Files and being able to see Dana Scully and see, as a little redheaded girl who was obsessed with aliens, watch a redheaded woman throw on a lab coat and fight aliens with science. And I loved her. I loved everything about her. And I just wanted to be her. I was lucky enough last year to actually do a panel with Gina Davis on the Scully effect and talk about that, the importance of representation on screen. And that's what the Gina Davis Foundation is all about. It's about gender and media representation. So it's a really fabulous organization. And yeah, Catherine Janeway as well was a big, I genuinely don't think I would have got through grad school if it wasn't for Star Trek Voyager, because I was just like, Janeway can do it, I can do it. I want to make Janeway proud. So that was it.
Yeah.
I think the interplay between science and science fiction really can't be understated, especially in the way that it influences us, inspires us to go ahead and get inspired. But there's continuous crosstalk between the two, or the people working in the sci-fi come talk to astronomers, people at NASA, get some ideas, try to extrapolate to the future. We look at what they're doing and say, well, you know what of this can we actually make happen? And I think it's a wonderful synergy and helps both the fields be better. If I may, I have a short story about inspiration myself. I'll give my age away here, but I was inspired by the original series Star Trek, so going back a ways. Along with the original space program, the New York World's Fair. There's a lot of stuff going on in my life that all kind of led me in the direction of a technical career. But there was one episode in the original series of Star Trek which finally tripped the wire, got me to go to the library and pick up an astronomy book. And once I did that, I was dead. It was just, from then on, I was going into astronomy. But that episode was Who Mourns for Adonais, which is when the Enterprise crew runs in to the Greek god Apollo, or at least a creature that says he is so. So that got me go to the library. They mentioned that they were in a certain star system, and I just wanted to find out if it was real. So I went to the library, pulled out an astronomy book, and say, yeah, Beta Geminorum, that's a real star on the sky. But I had gone through, pages of astronomy texts, and ended up walking out of the library with this book, and I went for astronomy ever since. The thing that has really blown my mind and really illustrated the closeness of the communities, though, is that more than 50 years later, I met the actor Mike Forrest, who played Apollo in that episode. And I've now had dinner with him a couple times, met, you know, some of the friends and things with him. And, you know, I'm just melting in his presence, and he's doing the same, meeting somebody from NASA. It's, you know, it's just kind of one massive love affair. And it's wonderful to see that happen. And there's a lot of a genuine love both ways.
There's also a fan fiction episode of Star Trek Continues where they continued that storyline in particular. So
you can be sure I watched that.
So a bunch of years ago when I was working at Sky and Telescope, I went out to California for a meeting, and I know Andre Bormanis, who was one of the science advisors at the time. And we asked him, do you think you could get us a tour of one of the sets? And so we got a tour of Deep Space Nine set, and you know, we're walking around in the Quarks bar, and we're looking at things, and they basically said, don't touch anything, it's a hot set, you know, but you can go in there and look around. And the two fellows that play the Ferengi walk up, Armin Sherman and Max Grodenchuk, and he introduces us, and I'm just geeking out, like, oh my God, I'm on the holodeck, this is so cool. And he introduces us, and Andre says, Carolyn works at Sky and Telescope. And these two Ferengi go, oh, that's really cool. And I thought, here we are geeking out over each other. It was just a really good moment.
Yeah, it's one of the nice things about being able to kind of turn to the sci-fi world for that inspiration, because, you know, the lack of role models in the real world is often pretty real and pretty harsh. And so, like Erin was mentioning, to be able to turn to the fictional characters, but you can still sort of set your sights on their goals and use them as inspiration and, you know, help give you direction. Or, you know, I know that Starbuck was definitely one of that for me, where it was just like, you know, she's a badass. She just does what she needs to do to get it done. And I'm like, I can see that being beneficial. And that was, you know, but they don't have to be real to be inspirational. And so that, I think that's one of the real benefits of this.
And it's also one of the primary reasons why we bring so many scientists to Fort Collins Comic-Con, just to show that the pathway is possible. There are real life superheroes out there doing science, and you can be one of them. So we have a question from Twitch. Domestic 6000 says, is there a space research project coming up that you're excited about, what the findings will be, and if so, what do you hope will be discovered?
So maybe I'll jump in with that one. I talked about this in my talk earlier today. I'm really excited to see what the results of the combination of the NSF's Inouye Solar Telescope, NASA's Parker Solar Probe, and the NASA ESA Solar Orbiter together do. So it's not one mission, but it's three together that are going to hopefully completely change our understanding of how the sun works. So unlike most astronomers, I know very little about anything other than the sun, but I know an awful lot about the sun. And so I am pretty focused on where my attention goes. And so there's so much about the sun that we just do not understand. And Cece asked me a question earlier about the coronal heating problem and why is the atmosphere of the sun 1,000,000 degrees when the surface is only 5,000? And the answer to that is, and we don't know yet. There's so many big unanswered questions about the star that we live in. Like, we live in the atmosphere of this thing, and we have so much that we don't know about it. So these three missions together are set to really transform how we see the sun, and B, how we understand it. So that's definitely the big excitement for me over the next few years.
Can you explain really quick what the difference is between all of them that makes them complementary? Or
yeah, absolutely, that's a great point. So the Inouye Solar Telescope is run by the National Solar Observatory, which is the institute I work for, and it's a ground-based telescope being constructed in Maui, Hawaii. It's almost done with construction. Hopefully it'll be finished in the spring of next year. And it's the largest and most powerful solar telescope in, well, we say in the world, but technically in the universe, because I assume there are not many other solar telescopes not on planet Earth. So the most powerful solar telescope in the universe
that we know of.
And we released the first images from the telescope earlier this year. It was the pictures that looked like caramel corn, and it was all bubbling away. And so the Inouye Solar Telescope, based on the Earth, is focused on understanding the sun's magnetic field and kind of the context of a lot of what the other two observatories will show. So Solar Orbiter is the ESA NASA mission, and it is going just over halfway towards the sun. I think it's about halfway, don't quote me on that, but it's not going as close as Parker Solar Probe will, but it has sort of a hybrid set of instruments that complement both the Inouye Solar Telescope and Parker Solar Probe. And meanwhile, Solar Probe is going much closer to the sun and will be sort of capturing a lot of in situ, so in place where it is, particles and field measurements, so electric and magnetic field. So a bit like, you know, putting your thumb up and measuring the wind as opposed to trying to do observations of it. So the three of these, it's basically one in place, one far away, and one in between. And so together, we're hoping just to bring multiple views of some of the big unanswered things. So one of the ones that will be interesting for scientists, perhaps less so for everybody else, will be why does the solar wind accelerate? So it leaves the sun and it's pretty slow, and sorry, my hands keep disappearing. Leaves the sun and it's pretty slow, and all of a sudden it gets much faster. And trying to understand why and where and when that happens is one of the big objectives, along with many others. So yeah, there's we haven't ever gone this close to the sun before, and we have never seen the sun in this much detail before. And so together, these telescopes are going to do some pretty awesome things.
I didn't mention earlier, that was interesting to hear you say that, Claire. I didn't mention earlier that my area of research is the outer atmospheres and winds of stars that are more evolved and cooler than the sun. But similarly there, we're trying to figure out how the heck the wind gets accelerated off the surface and pushed into deep space. So if you find the answer first, you know, a little phone call, that'd be
Absolutely.
great. And we're certain that'll work for the warmer evolved stars. Probably have a very similar mechanism as the sun. The cooler ones probably use a completely different mechanism. So it won't solve everything, but it'd be a great step.
It's a good start.
I think on the astrophysics side, what I'm looking forward to, there are two great observatories coming in the future. Next year, hopefully around Halloween, the James Webb Space Telescope will launch. And this is a facility that's much larger than Hubble. It's 18 segments together to have a 6.5 meter diameter. And the idea there is to get the same kind of resolution that Hubble has on the sky, but do it in the infrared at longer wavelengths, where you need a larger diameter mirror to get that same kind of resolution. So I'm very excited about that. But if you're asking what I'm most excited about, it's the one after that. Now, I may be slightly biased because I'm working on the one after Webb. I kind of jumped from Hubble. I worked on Hubble and I jumped over Webb. Let them take care of that. And I'm working on something called the Nancy Grace Roman Space Telescope. And that actually uses a mirror the same size as Hubble's. So it'll get the same, match the resolution of Hubble, but it's designed to work mostly in the optical and infrared. And it's designed to be a little bit more like a pair of binoculars than a telescope, in that it has a very wide field of view. So when it looks out on the sky, it will see 100 times the area on the sky in a single picture that Hubble gets. So we'll be able to do these incredibly large surveys of the infrared sky, super efficient. We'll be able to study the structure of external galaxies. As for example, there was a Hubble program to look at the Andromeda galaxy, our nearest spiral galaxy neighbor. It took 430 pictures stitched together to do a survey of 1/3 of the galaxy. Roman will do that in 2 exposures. So instead of spending a month getting data for this thing, you go out there and say, oh, let's take a couple pictures. Okay, next. And we'll be able to do that for a whole bunch of galaxies across the sky. And we'll be able to do temporal studies of changes in Andromeda that we'd have no hope of doing with Hubble. So that's all very cool by itself. But the main goal of Roman is to try to understand dark energy. And that right now is probably the biggest puzzle in modern astrophysics. We always thought for many, many years, and I grew up with the concept that the universe is expanding, but it's slowing down with time. And the only question was whether it would just kind of gradually fade out or whether it would come back together in some big implosion. Never did we really consider the possibility that it might accelerate. It turns out the universe expanded and slowed down for the first 5 billion years or so, and has now, we realize, been accelerating. So it's like you took an apple, threw it up in the air, and instead of slowing down and coming back to you, it started going faster. We have no idea what's doing that. So we call it dark energy. Dark as in mysterious, not because it's black or we can't see it, but we don't know what it is. So, maybe it's magic, maybe not. I don't know. Maybe it's the energy of the vacuum. But that to me is the most exciting thing we can do. And I don't know if Roman by itself will be enough to figure it out. We're going to try to observe the consequences of dark energy, really pin down the expansion rate and see any other empirical evidence we can of it, and then hand it over to the theoretical people. And I hope there's somebody out in the audience there that's really into physics and theory. And we're going to say, here's the data, here's what this funny universe is doing, you explain it. And so that's what I'm looking forward to.
Isn't that the same? Isn't that some part of the mission for the Vera Rubin telescope in Chile?
Yes, it is, and we hope to work very carefully with them. There are differences in design which make one facility better at certain kinds of observations than another. There's more than one way to study the acceleration of the universe. So Rubin and Roman, just to be complicated now, they had to name them after two people, both starting with R. Hopefully putting it together will give us an answer more quickly and more precisely than either one of the two observatories by themselves. And that's true in a lot of what we do in modern science. Things are getting more and more collaborative as we go on, especially as the facilities get larger. You can't let Claire get all the time on Roman because the rest of the world wants to use it too. So the way to get time is to say, okay, well, I'm going to invite Erin and Carolyn and Ken, and now we've got this big group, and look at the whole world wants to do it. So you have to give us time on this observatory. And sometimes that works, sometimes it doesn't, but it's better often than going in by yourself.
Dr. Erin?
Yeah, I mean, I think we're all exposing our biases in the best way. But I'm just thrilled by what LIGO's been discovering. So LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And that is, like I said, that's what I worked on. But basically what it is that they've been able since end of 2015, they announced it in 2016, have been detecting ripples in our universe, in the fabric of space-time, from colliding black holes. And even just that one first discovery put a big check mark next to a lot of stuff in physics. It just, it was like, okay, we just observed black holes merging. We're discovering black holes merging that are in a mass region that we hadn't seen before. We're discovering gravitational waves, that they are traveling at the speed of light, that they are emitted from these changes in space-time. And we're detecting the motion of space-time itself. Our universe itself is expanding and contracting with these ripples, but it's incredibly small. The science that's gone into it is just crazy, because the detectors are sort of 4-kilometer long arms, and they're detecting changes in those lengths that are 1/1000th the size of an atom. And so the level of precision that has gone into LIGO, and the amount of technical design and the amount of research and data analysis and statistics and data processing that has gone into it is just phenomenal. And even so, that one detection, awesome, amazing, fit the bill, checked all the boxes. The theory matched the observation brilliantly. But since then, it was like boom, 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 boom. Like, you kept seeing stuff, and so our knowledge of the universe is just increasing unbelievably. The analogy I like to use for this is, it's like with all of these other telescopes we've been using, we've been seeing the universe. We've been using the electromagnetic spectrum to study the universe, whether it was radio, X-ray, gamma ray, visual, optical radiation, infrared. All of that is part of the electromagnetic spectrum. This is like bold, italic, underline, we're hearing the universe for the first time. It's not sound, it's not literally sound, but it's like a completely different sense. So we've been, being able to hear for the first time, or not having seen anything and just relying on your hearing. This is a whole new sense to the way that we're detecting the universe around us. And so there's going to be a lot to learn, and it may start to fill in holes with like dark matter, which we know interacts gravitationally, but doesn't have an electromagnetic component to it. So I'm really excited to see what the continued study of our universe through gravitational waves will teach us. They're currently on hold with their observations just because of the current virus situation, but once they get up and going again, we should start to get more. So it's very exciting. I can't wait to see what we learn.
And I'm with you on that, Erin, because I think we have to emphasize how rare it is to get a brand new observational technique like this, where you have something that didn't exist a couple of years ago, an entire new way to sense, to remote sense the universe. And it blows my mind to think of, I mean, we're just privileged to be alive at a time where something like that happens.
Mhm.
DH on Twitch has asked you to expand
wait a
on
minute.
ripples, Dr. Erin, if you could.
Oh,
That's a great
Go ahead.
question. Sorry, I was muted. So what we mean by the ripples is really just the expansion and contraction. So we use that trampoline analogy, right, to talk about our universe and how space-time works. You put a bowling ball on, it curves down. That's kind of how gravity works. And so you can think of these gravitational waves as ripples in a pond from, dropping a pebble in, they go out. But really it is in 4-dimensional space-time. And so what it does is it's this expansion and contraction in this, we call them quadrupolar waves, but it literally just takes space, and you can kind of more visualize it like compression waves. And so that's why they use this interferometer, because as a wave passes by, one arm gets shorter, one arm gets longer. And then that laser beam that's going in each direction is now traveling a slightly different distance. And so they create an interference pattern when they bounce off the end and come back. So it's pretty cool. I hope that makes sense. Yeah, thank you for the clarification.
No, that's a great answer. And that's really one of those things that when you use the idea of sound, it really kind of brings it across, although it's not really sound. As a radio astronomer, you would never say that, but that actually kind of leads to what I think I'm looking forward to, which is in February, we're going to land Perseverance on Mars. And I talked a little bit about this yesterday, and it's going to be the first spacecraft that has a microphone on it, talking so that we can hear the wind. Probably that's probably all we will hear, but we've never listened to a planet like this before, and so that will actually have a real microphone on it. That's kind of a short-term thing. In the long term, I'm really looking forward to the first human Mars missions. And since 1983, I think I've been following Mars missions and the sort of the progression of missions that have been going out. And every time that we've had like Case for Mars meetings or things like that, we've said, oh, we're going to have people on Mars in 1995, or we're going to have them in 2005, or maybe it's going to be 2020. Well, here we are in 2020, and we don't have people on Mars yet. And it speaks to a number of things, but I think one of the biggest factors is it's going to be darn hard to get people on Mars. We've had 70 plus missions going to Mars, and not all of them made it. I've heard some people privately refer to it as the death planet. It's where missions go to die. Well, not all of them do. We managed to get it right, and I have to give all credit to the Indian Space Agency. They got to Mars on their first try, whereas the U.S. and Soviet Union had a few prangs, here and there, and other spacecraft along the way haven't made it, or they've blown up before they got there, or whatever. But the ones that have gotten there have really given us this great look at the planet. It's given us some look at the geology. It's done the rock sampling that a geologist would want to do. It's sampled the atmosphere as much as it can. All of the information that we need that you would send a scout forward, to look for in an Earth-based mission. These guys are giving us, these little robots are giving us, and it's giving us some sense of what we're going to need to do to prepare to go to Mars. So yeah, we didn't make it this year, and we might not make it in 2030, but all of this information we get from all of these missions is going to be what helps those first Martians be really prepared, because they're going to be moving to a planet that doesn't have any air. The water is frozen underground. They're going to have to make their own oxygen, nitrogen atmosphere. They're going to have to dig for the water or make it themselves, planting food. I mean, there's going to be a number of things. The movie The Martian is a pretty good example. I mean, there's a few kind of weird things in there, but it's a pretty good look at what it would be like to be on Mars. And I think those first people that go, whether Elon sends them or China or the US or a whole multinational group, are going to be kind of a metaphor for change in the human race. We're not going to just be stuck on one planet anymore.
Can I jump in with this for a little bit as well? Because not only are the challenges with being on Mars, but getting to Mars is even a major challenge.
Absolutely.
So the issue of space weather and the radiation that people are exposed to is going to be a really important question. And you are basically damned if you do or damned if you don't. You either go during solar maximum when you have higher chances of large coronal mass ejections, or you go during solar minimum where your coronal mass ejections are lower, but then your cosmic ray count is higher. And so trying to figure out when that sweet spot will be is a big question. And then ultimately, and this ties into one of the questions that we got in the chat, which I'll answer at the same time, if that's okay. Ultimately, when you're on Mars, you have no magnetic field to protect you from this space weather effects either. So one of the questions that we got in the chat is what happens if we flipped the magnetic field on Earth? Well, the role of the magnetic field on Earth is really important to us, and it's mainly that it protects us from space weather effects and space weather impacts. So because we have a magnetic field and we have a nice thick atmosphere, it means we can live comfortably on Earth. We don't have to worry about solar eruptions or any of these major things coming from the sun. And so this is a big part of why we can live on Earth, but Mars has only residual magnetic fields. They have these little umbrella pockets of magnetic fields all over the surface, but they're not particularly robust. And so they don't do nearly as good a job at protecting future potential inhabitants from the sun. And so we mentioned this as well, that the effect of the star on a habitable planet. So earlier on, we talked about the idea that you could have Earth-like planets around other stars, but if the stars themselves don't allow for habitation, then the Earth-like planet is neither here nor there. And so in some ways, Mars is a good example of this, where because it doesn't have that inherent protection, the impact from our star is going to be much more important. And so to answer the question about flipping the Earth's magnetic field, I think if it was like a light switch and you could just flip it right away, I don't actually think there would be a huge amount of impact. You know, your compasses would now be back to front and so on. There'd be that kind of thing. I think the bigger issue is how the flip might happen. So first and foremost, I want to preface this with this is all hypothetical. This is not a prediction. There are many, many theories of the Earth's magnetic field will flip, and I'm not necessarily a proponent of them. That's not what I'm trying to say here. So we're just playing a fantasy game right now. So I rooted out some styrofoam balls because I think it'll be easier to explain with this. So the Earth's magnetic field looks a bit like this. It's a bit like a butterfly wings. Actually, if the sun is on this side of the Earth's magnetic field is all drawn out like this in a teardrop shape, but we're not going to worry about that for right now. So if the Earth's magnetic field were to flip, so it always had this loop facing the sun, so if it flipped this way, I think things would be pretty okay, because the issue that we would have with the sun, the impact from the sun, is that the round bit of the Earth's magnetic field is like a shield, so it protects us from those incoming particles and high energy events coming from the sun. So as long as that shield stay there, it doesn't quite matter if it rotates this way. However, if it rotates this way, then all of a sudden when we're in this orientation, we have this funnel straight from the sun into the upper Earth's atmosphere and into the area of the poles. And so that is where things might get a little bit dicey. So again, completely hypothetical, not happening, not a prediction, but that would be the issue. So the question is more how it would flip and how long it would take. And what would the other question that I don't have an answer to, but maybe somebody else on the panel is what's the mechanism that would cause it to flip? Because the reason for the Earth's magnetic field is our molten core. The reason for the sun's magnetic field is the fact that it's a plasma with free electrons moving. And when you have a stream of electrons, you have an electric field. And when you have an electric field, you have to have a magnetic field. And so that's why the sun has a magnetic field. But and it flips every 11 years. So this is why we have a solar cycle. So the orientation of the sun changes north-south to south-north every 11-ish years. But the mechanism for the generation of the sun's magnetic field is entirely different to the Earth's. And so that's an important factor. So I don't have a good reason to understand why the Earth's magnetic field might flip, but it's a good hypothetical question.
You know, there is evidence that the field has flipped over Earth's geologic history. I mean, you see it in the rock in the rock record. And so maybe, and I don't have a good answer for it either. I don't think anybody really knows, but maybe the idea is to look at, try to figure out what conditions were with the Earth, particularly the interior at the time of those flips. And that's like geologic history, you know, on steroids. So.
We're one scientist short of being able to answer the question. That's really
right.
What's happened here. Next year, bigger budgets, going to bring in all the rest of them.
Yep.
Where we got all the fields represented. That's what's happening. So going back to gravitational waves for 1 minute, Dr. Erin, a watcher on Twitch has asked, what is the significance of each particular ripple, or do you need a bunch of them in order to measure the speed of gravitational waves? Can you just get it from one, or do you have to see a lot to?
Yeah, so that was kind of where, when I said I started in continuous gravitational waves and then moved into gamma ray bursts, a lot of that was within the field of gravitational waves. We can think about them kind of broken up into a grid shape that you can talk about like the sources. Some of them are going to be what we call transient. They happen and then they disappear. Others are continuous. And then within each of those, you have their continuous and modeled, or transient and modeled, or transient and unmodeled, and then we don't know anything about it. They're happening all the time, but we have no model for it. And there's different sources that fall into each of those categories. And so for the ones that are modeled, where we know what they should look like based on the equations for general relativity, that starts to give us clues where all the different things we can learn about them. And the question about the speed of light, that was always a big question, was, okay, the math says, just purely when you take Einstein's field equations for general relativity and perturb them a little bit, so yeah, create a dynamic in the field that's going to, and then you propagate all the math out, you end up with a wave equation. That's where Einstein said, okay, there are these gravitational waves. And you could see in that wave equation, the velocity is c, it's the speed of light. So that was one of the things that we wanted to answer. Okay, if we see these ripples in space-time, do they travel at the speed of light? And the only way we could know that is if we also got a signature from an event that happened in the electromagnetic spectrum, because the electromagnetic spectrum is light, so it travels at the speed of light. And if we found coincident detection, so we saw, for example, a transient event that was modeled. So in this case, the collision of two compact binaries, either two neutron stars or a neutron star and a black hole, if we saw that accompanied with electromagnetic light, that could answer that question. And in fact, that's exactly what we did see. There was a gamma ray burst that we got in the electromagnetic spectrum and saw a modeled gravitational wave signal that happened at the same time. So that was sort of like, check that box. And they travel at the speed of light. And then all the different details that we get. So when we see these gravitational waves, it's not just one ripple. We see this spin up that happens. There are these stages of the black hole collision. They're spinning towards each other. We call that the in-spiral phase. Then we have a merging phase, and it's kind of like, that's kind of what it sounds like. If you convert it into an audible frequency, it spins, the frequency increases. So you get this, and then you get this ring down phase. So after that black hole is merged, it kind of settles into its spot. And when it's doing that, it's just has these little residual gravitational waves. And so all those waves, like how quickly that happens, whether it's like, or those little details unpack things like the mass of the two objects, how far away they were, all the energy involved in it. So lots of great information. And I can see all the gravitational wave questions coming in too. I will take a back seat because we're nearly at the end, but I appreciate all the details, and you can find me at my handle to follow up on those. So thank you.
So we do have another question. Ryan and Clara, how close could we get to the sun with our current technology, and how do you keep people safe from solar radiation?
Well, 2 years ago, a probe called Parker Solar Probe was launched by NASA, and it is going to travel to within almost 4 million miles of the sun. So given that the sun is 93 million miles away from us, it's like 96% of the way to the sun. So it's almost right there. It's going incredibly close, closer than anything we've ever sent before. Now, this is an unmanned mission, so there are no people on board. But that, I think, is about the closest that we can possibly contemplate right now before the temperatures start to get so high that things are insurmountable. One of the strange dilemmas that they have actually is not even so much the temperature on the sun side, but it's the difference in temperature from the sun side to the back side. So they have a big sun shield that protects all the electronics and delicate instruments from a lot of the intense heat, and the difference in temperature from the front side on the one side of the sun shield to the other side is so huge that a lot of warping and things like that needs to be managed in order to make sure that things stay pretty stable. And then I see another question about how do you keep people safe from solar radiation? What they do in the space station right now is they have people hiding behind their waste. Water is one of the best ways to protect them from space radiation. And so having a big wall of water, in whatever capacity water might appear in this case, is a great way to try and block a lot of that powerful radiation.
Yeah, if there are any Avenue 5 fans, that wetsuit in Avenue 5 is absolutely true.
Spot on. Yeah.
So what
I think that's
is,
one of the big things
Oh.
that we have to worry about, as you said, on for a trip to Mars. The other thing that the radiation is really important. I mean, that's you have to practically build a lead-lined spacecraft, which is really going to cost you a lot in terms of mass and boost. And then the other thing is gravity. I mean, you're going to have people, for 3 or 4 months at a time in microgravity. Essentially, we're going to have to, we don't want them arriving as Odo, in a bucket. They really have to kind of be people. So we have to figure out some way to, save them in some way, like some sort of little bit higher gravity environment. And that's going to be a technology we'll have to develop at some point.
So one last question. What is the most surprising thing that you've learned in your field? And this is a big question. So you can, you can answer it to whatever degree you would like.
Well, I'm not in the field anymore per se in research. I'm writing a lot. And so there's 2 answers to that. One of them is that there's always a story to be told. I always thought, oh, we already know all the stuff about the solar system and the galaxies. Well, we don't. So there's always a story to be told. In the area that I used to study when I was in graduate school about comets, I think that we're still finding out about the solar wind by using comets as a solar wind probe. And I keep up with the literature on that. And people are now finding little variations in the solar wind that we didn't actually see before. And so the comet's telling a lot, and getting these close-up views of comets has really taught us a lot about, how they're reacting in situ. If you're standing on the surface of Churyumov-Gerasimenko, you kind of see these jets coming out, and that tells you something about it. So that kind of blew me away when I saw those pictures.
I can answer if other people are still thinking.
Yeah.
So for me, I think scientifically, one of the things that I really loved learning about was gamma ray bursts and neutron stars. I think so. Neutron stars are these dead remnants of massive stars that weren't massive enough to become black holes. So you have this really condensed matter. It's basically the mass of our sun condensed down to the size of a large city. And they're weird, cool objects. We've observed them before as pulsars, so kind of like lighthouses that are sending us this regular radiation, and they act weird sometimes. So that regular periodic radiation sometimes just goes really fast and then starts slowing down again. So when we were asking about, could the magnetic field flip or could the magnetic field on Earth change, that's where my mind went, because we studied so much about the fluid dynamics inside neutron stars and is there pinning that's happening? Is the fluid getting stuck somewhere and then it's suddenly coming loose and you get this spin up with this neutron star? And so there's a lot of outstanding questions with that. And then of course I love apocalyptic movies. And so this idea that, gamma ray bursts are, one of those doomsday scenarios and an answer to the Fermi paradox of, if there's so many planets out there in other star systems, why haven't any contacted us? We know we're not there yet, but why hasn't anyone else contacted us? And then it's just kind of that fatalistic, nihilistic answer of well, you're more likely to get wiped out by a gamma ray burst than you are to reach warp technology. But then we cry and then we go watch some Star Trek and possibly imbibe some Romulan ale, so we're all good.
Dr. Ken?
Well, I think the most surprising thing has to be the discovery of dark energy and the acceleration of the universe. But we already talked about that, so I'll just throw in a second one, which was, I don't know if it was a surprise so much, but a very important result of Hubble observations, and that was the actual acquisition of evidence that black holes are real. They were a theoretical concept before Hubble was launched. Hubble not only found empirical evidence that black holes exist in the real world, but then went on to discover that the size of the black hole, that they exist in nearly the center of nearly every galaxy, and that the size, the mass of the black hole is correlated with the mass of the galaxy. Larger galaxies, larger black holes. So maybe not too surprising, but And we also discovered that these are what are responsible for activity. I talk about active galactic nuclei, some galaxies where there's huge amounts of energies pouring out of them. And we have only recently, we've made some observations that have shown what happened when that active black hole at the center of a galaxy turns off. And it turns out that an active nucleus kind of controls the environment, keeps it pretty warm in the vicinity, and not a lot of star formation goes on after the central nucleus turns on. We have recent observations that show if the central active engine turns off, you can get these bursts of star formation where just hundreds of thousands, millions of stars start forming like crazy in the galaxy because the gas can finally cool down enough to coalesce into stars and planetary systems. And that's just really cool. It's almost like well, it's alive. The black hole can kind of regulate the galaxy and keep it in an even keel. You turn off that regulator and things just go bonkers for a while.
Dr. Claire?
I think the thing that surprised me most is sort of a non-answer. It's the fact that there's still so much that we don't know. The fact that we have no real strong understanding of why the sun's atmosphere is 1,000,000 degrees and we live so close to it and it's right there and it's a part of our everyday life and we don't know. That is a surprise to me constantly, of all the things that are left unanswered. So there's plenty of work to go around if anybody's considering a career in this field. Come join us.
And more reason
Maybe
to
in my
have you
next
guys
life.
back next year.
Maybe in the next life.
So I want to say a huge thank you to Cece, to Dr. Claire, Dr. Ken, Dr. Erin. Thank you all for being here. Cece, thank you for bringing all the scientists together for us this weekend for an amazing series of science panels. Jeff, thank you in the behind the scenes for moderating and managing all the comments, questions, and the streaming to all of the different platforms. And we hope that you have really enjoyed your time here at Fort Collins Comic-Con 2020, the streaming edition, and that you've learned a lot. And quickly, in case folks wanted to get in touch with you or follow up with additional questions, where can they find each of you?
Easiest place to reach me is claire@nso.edu. You can also find me on Twitter at Claire Raftery with no E on the end of my name, CLAIRAFTERY. That's probably the easiest way to find me.
Dr. Ken?
Sorry.
You can follow me on Twitter at Ken Astro. Is the easiest way to stay in touch, although be warned, if you follow me there, you'll get fairly large amounts of Trek and Disney and sci-fi in general, as well as actual astrophysics. But we try to mix it up from time to time. Oh, and Renaissance festivals too. So you'll get a mix of things if you come after me.
This is why we're friends, Ken.
Cece?
Yeah, wait until he drags you to Disneyland, Aaron, or Disney World. I mean, he had a spreadsheet, you wouldn't believe it, of all the things we were going to do. You can find me at thespacewriter.com. That's my website. It's all one word, thespacewriter.com. And I'm at thespacewriter on Twitter.
And Dr. Erin?
You can find me at Dr. Erin Mac, most everywhere, DRERINMAC. If you're watching here on Twitch, that's also my Twitch channel. And my YouTube, if you just search for Erin MacDonald on there, MAC, small d, Highland Way. You can find me. You can find all my videos there as well, and drerinmac.com, and then mostly on Twitter as well. And I'll be taking a little bit of a backseat in the coming months when Discovery starts airing. But I can't wait to talk about it once the season's finished. So thanks. And thank you for having me, Nick, and donate to the public library.
Yeah,
Yes.
as it should be noted that this year, by about this time, we would have raised about $20,000 for the Poudre River Public Library District's children's literacy efforts. And thanks to COVID and other mitigating factors, we haven't been able to do that. So thank you to all the folks who have donated so far and to, attend the virtual con and donated in that way. And so we appreciate you. We appreciate all the scientists that have joined us, and stay tuned in September for some really, truly amazing artists. We're going to be collaborating and working with some artist creators and highlighting all of their amazing work as well. And I believe Cece's going to be joining us at some point during that as well with some really cool stuff. So I look forward to the extension of this virtual Fort Collins Comic-Con and we will see you out there.
Thank you. It's been a
Thanks for
pleasure.
having us.
Great to see all you guys. Great
Yep,
to be on a
thanks.
panel with you all.
Bye.
Yes, likewise.